Hello student, welcome back to A-Star Tuition channel. Today we will complete our discussion about circular motion and gravitation. Specifically, we will talk about orbital motion. Let's just start. Now, the discussion about orbital motion usually start with the notion of the planetary motion, or moon orbiting around the Earth, for instance, or any satellite. Now, let's say that this is the Earth, and orbiting around the Earth is the moon. Like you have a moon over here, like that. And let's say that the distance between the center of the moon and the center of Earth is equal to r. Now, in this case, we know that again, you have to understand one thing, that even though the universal law of gravitation works for point particle, let's just assume that the distance between the moon and the Earth is actually quite far, that you can assume that it's a point particles, right? Now here, obviously, it doesn't seem like they are point particle, but this drawing is not based on scale. Now the force between them is equal to G ME mm over r squared. So ME is the mass of Earth and mm is the mass of the moon. So the gravitational force is equal to this. Now the thing is that when the moon is orbiting around the Earth, then this is in the approximately circular motion. So remember that the motion is in reality it's actually not circular, but it's actually a bit elliptical. But for a lot of approximation, this is quite good. We can assume this is circular. And for circular motion, the object that experiencing or is undergoing circular motion will experience centripetal force, as we discussed in the first video. So the centripetal force is the mass of the moon times the speed of the moon over r squared. So since this is since for the moon, this gravitational force is the gravitational force between it and the moon. The gravitational pull from the Earth is what caused the moon to orbit around it. So therefore we set this equal to each other. So G, mass of Earth, mass of moon, over r squared equal to mass of moon, v squared over r. Now you see that if I were to cancel mm and r here, we wound up with v equal to the square root of gm over r. Now this is what we call as the orbital speed of the moon. Orbital speed. Now please understand that here I'm using the example of Earth that is stationary and that the moon is orbiting around it. But it can also work for the case of, let's say, the Earth is orbiting around star like the sun. So this is the orbital speed. Now when you look at orbital speed here, you can actually relate it to what we call as the period. Now, remember, for every circular motion, uniform circular motion, there is a corresponding period. Now in order to calculate the period, what you can do is that period of the time is equal to one full circumference of the circle, which is 2 pi r, divided by phi, and phi is this. So the P is equal to, or the period is equal to 2 pi r over the square root of gm over r. So this is the period. Now notice that in this case, you see that it doesn't depend whatsoever on the mass of the entity that is actually orbiting. It's always a function of the mass of the stationary entity, which in this case is the Earth. Yeah. Now here, even though this is the relationship, this is the equation to find period. If we were to do something here, let's say we square both sides, and then we have t squared times gm over r equal to 4 pi square r square. Yeah. So in this case, the t square equal to 4 pi square over gme times r cubed. Now, so that in this case, you see that the square of the period is proportional to the cube of the radius. So, in other words, if you have another entity, maybe another satellite that orbits around the Earth, then you can compare the period of this satellite compared to the moon by comparing the radius. So in this case, the period goes like r to the 1.5 power. Yeah. So it means that if the radius, let's say, becomes, if the radius is double, then not double. Let's say if the radius is 4 times, then you substitute 2 square power of 3, so the period becomes 8 times. Yeah. So this is an important relationship. Hopefully you understand this. Now, this is the summary of what we got previously. But with this, we actually want to find the, we want to quantify the energies related to orbital motion. So remember, we have potential energy, the gravitational potential energy, the kinetic energy, and the total energy. So let's talk about the gravitational potential energy first. Yeah. So from the previous video, the formula is this, yeah, minus g m over r. Yeah. So let's say that the stationary entity is the one with capital M, and the the moving or the orbiting entity is the one with mass lowercase m. Yeah, so minus gmm over r would be the gravitational potential energy between the the gravitational potential energy of the orbiting satellite, or any practically any orbiting entity. Yeah. Now this is the GPE. Now what about for the kinetic energy? Now for the kinetic energy of the orbiting entity, you can actually calculate this by using the equation half mv squared. Remember, I'm using the lowercase m for the orbiting entity, the moving entity. Okay, so, but then the speed is the orbital speed, which is this one. And so let's calculate, let's substitute that, gm over r, and then I square it. So this is going to give you gmm over 2r. Now, this is the equation then for the kinetic energy, right? So you can see that they have more or less similar form. Yeah. The only difference you can see right away is that this is like positive and this is negative. By the way, this is important. Kinetic energy is always zero or positive. Yeah? It never negative, because it involves the square of speed. Now, so GPE is this and kinetic energy is this. So then this is like twice. The value of the GPE is twice as much as this, but it's negative, yeah? Whereas this is positive. Now what about the total energy? The total energy, well, in this case, the total mechanical energy. Yeah, I don't really have to write down the word mechanical. Yeah, in this context, because if it's not ambiguous, then you can just write down total energy. Let's just equal to the gravitational potential energy plus the kinetic energy. So this is going to give you minus gmm over r plus gmm over 2r. If you simplify the expression, it's going to give you minus gmm over 2r. Okay. So this total energy is equal to that. Now you can see that this is actually the negative of the kinetic energy. So this is negative of the kinetic energy, or is equal to half of the GPE. Now in order to better understand this in like using like graphical method, so I think it's better if we to sketch the energy function of R. Yeah, remember R is simply the orbital radius. Okay, so for the kinetic energy, it is proportional, inverse proportional to R. Yeah? So obviously I assume that the two masses doesn't change during the orbital motion. Yes, so the two masses don't change. So here, yeah, this is the graph of the kinetic energy as a function of distance, and then for the total energy is this. Yeah. So this is, let me label this. This is for the kinetic energy. And this is the kinetic energy, K. A. This is the total energy. And you can see right away that the value is, this is like the total energy is minus of kinetic, so it's symmetrical with the horizontal axis. Now the GPE is twice as much as the total, so it's gonna look like this. Yeah, so this is the total. I'm sorry, this is the gravitational potential energy. Okay, so this gives you the relationship between what kinetic, the relationship between kinetic, total, and GPE as a function of orbital radius. So in orbital motion. Now, so with this graph, you can, like see that you can deduce something like, for instance, if the orbital radius is getting smaller, I mean, if they're getting closer to each other, the kinetic will increase, yeah, and then the total will decrease. Likewise, the GPE. But you have to be careful. Even though this shows that the kinetic energy increases when R decreases, sometimes it depends on the condition. Like for instance, let's say that you have a planet and then this is a satellite, yeah, or maybe a planet that is orbiting around a star, like that. Now, the planet that orbit around the star, in this case, the planet is the orbiting entity and the star is the stationary entity. Now, when the planet is orbiting around the star like this, it has a certain kinetic energy, total energy, and gravitational potential energy, right? Then what happens if this planet is like, there's a collision, small collision with like some rock, some object, small relative to the size of the planet. Yeah. Now what happens is that collision will actually reduce the total energy. So reducing the total energy, meaning that it will move. The total energy will decrease. When the total energy decrease, what happens is that the planet will move to you can see the R will decrease, so it will move to a shorter radius. So this radius is shorter, yeah, compared to the previous. So remember, this is the new radius, this is the old radius, because of the collision, the total. Now, with the collision, so moving to smaller radius, meaning that, so what does it mean? Mean that the kinetic energy will increase. So it might sound a bit counterintuitive, yeah, like, oh, you hit with something. You hit with something. When you hit with something, obviously, it will slow down. Well, the thing is that it is slowing down initially, but then that slows down also cause the total energy to decrease, and then it also force the total energy decrease. That means that it will move to a closer orbit, so the R is less. Now moving to closer orbit means that the kinetic energy will increase and the GP also decrease. Yeah. So hopefully you understand the concept of energies in the context of orbital motion. Last, I want to discuss about the notion of escape speed or escape velocity. So let's say that you're trying a small experiment, like you throwing a rock, yeah, and then you impart an initial speed to the rock, and then you see that after some time it will reach maximum height, and then it will fall back down to Earth. And also do this, yeah, if you actually impart greater initial speed, what happens is that the rock will be able to reach higher distance before it reach, before it go back down, right? Before it falls back down. So the greater the initial speed that you impart to the object, the higher the object will be able to reach before it finally falls back down. Now, do you know that there is actually a speed in which, yeah, initial speed, yeah, if you try to throw like really hard, eventually the object will never go back down to Earth. There is a speed. Now that speed is called escape speed of the Earth. Now the value of the escape speed for Earth is actually quite high, so then it's virtually impossible. It's actually impossible for to be done by a person. Yeah, so you can't do that because the amount of speed is, I think it's in the order of 10 power 3 or 10 power 6 meters per second. So it's quite, the value is quite huge. Now, but then it raises actually interesting question, which is if you have like a large body of mass in which, so large that the gravitational pull will allow object to be bounded by that. Like this is like the moon, yeah, the moon. So then you have, any object on the moon or Earth, yeah. So large body of objects. So they are attracted by the gravitational pull so that it's bounded on the surface of the moon or of the Earth. Yeah. Now, this thingy, this what you call, let's call the heavenly bodies, the large mass of object concentration, concentration of mass. They have what we call as, again, escape speed or escape velocity. So in other words, you can actually apply initial speed to an object at the surface so that eventually it will, it will move up and it will never return to the surface. So then let me probably best define it. Yeah. So escape velocity is usually for a planet. Yeah. So let's discuss in the context of the planet. Yeah. Now in this case, the speed of velocity doesn't really matter anymore, yeah, because we actually want only the magnitude. So you can write the word velocity and speed is now used interchangeably in this case. Okay, so escape speed is of a planet. Yeah. So it's like the initial velocity or the initial speed at the surface of the planet, yeah, imparted on any object, yeah, such that the object will escape the influence of the gravitational field created by the planet. Okay, so escape the influence means, i.e., the object will not return will not return to the planet. Okay, so that's why the word escape speed is actually fitting in this case, escaping. Yeah. Now, in order to find escape speed, you only need to remember the condition. The condition for this is this. The condition, it has to be that the total energy, kinetic plus potential, must equal to 0. The reason why this works is that, imagine this is the initial, this is the kinetic and the potential at the surface. And then you impart, this is the kinetic plus potential at the surface once you impart the object. Once you apply the initial speed to the object. Now later, once it reaches far away, that it stops. It stops and does not return. In that case, the kinetic has become 0 because it stopped, and the potential is also 0. And the reason why the potential is 0 is because it moved very far away. Remember, the GPE function R looks like this. Yeah? So then if the orbital radius is very large, goes to infinity, then the value of the kinetic, the value of the GPE become close to 0. So therefore we write it down as 0. Yeah? So this is not really an exact equation, but it is approximate. Yeah? Because at far away distance, the GPE becomes negligible. Yeah? So then, what is the kinetic at the initial, after you impart the initial speed to the object at the surface? It's equal to half gm m over r. Now remember the formula for kinetic energy, gmm over 2r. But here I'm used this radius, the orbital radius is exactly the radius of the planet. Yeah. So if this is the planet, yeah, so r. Yeah, I thought I mentioned that this was moon, but then imagine this is a planet. Yeah. So the radius is r. So we use r as the orbital radius. And here the potential is minus gmm over r. Right? Okay. Oh, actually, you know what? Sorry, there's a mistake here. I cannot use this equation here because it's not an orbital motion. You throw it, so it's this. So only for orbital motion can you use kinetic as gmm over 2r. But the potential is still correct, because remember, the object and the Earth is separated by r. Okay, so the kinetic is half mv squared. Now in this case, the speed is called escape speed. So I think I have to mention that modify a bit. It's not just the initial speed, but the minimum initial speed at the surface of the planet imparted on any object, so that the object will escape the influence of the field created by the planet. Okay, so in this case I set this to 0, and then I can solve for the escape speed. This m cancel, so the escape speed become 2 gm over r. Now remember that root of that, and r here is the radius of the planet, and m is the mass of the planet, and g is the universal constant of gravitation. Now as you can see, it does not depend on any of the the mass of the object. Yeah? So what matters is the mass of the planet. Okay, so using this you can actually calculate escape speed of Earth. Yeah. So remember, g is a known constant. You know the radius of Earth, which is about 6,380 kilometers. Mass of Earth is about 6 times 10 power 24 kilogram. Put them in your calculator and calculate, and you'll find what the escape speed of Earth is. Okay, so that's it for our lesson today. And this lesson actually concludes the series of the circular motion and gravitation that we started from first video and until this one. I hope these videos give you a deeper and more understanding about the concept of circular motion and gravitation. Please like, subscribe, and share the video. I'll see you again next lesson.